Oh, thank you very much. It's really my honor to give a lecture here. I was here as a student like you 10 years ago, actually. So it was my pleasure, and Florence is always a special place for me. Okay, so in this course will be about the dynamics of 4D n equal to 1 gauge theories. So what does the dynamics mean? So here we will start looking at basically field theory in general. Assume that it have some gauge field. And we will study renormalization group flow, okay? And see at the end of the flow in the low energy, what happened to this theory? What are the quantum behaviors of this theory, okay? So this is the point of the lecture. So the emphasis will be on the dynamics part of the field theory, which I think is a very, very interesting part. And that's why we have a course on this. However, if I spend most of the time on the dynamics, one thing that I have to sacrifice because of the limited time is that I will omit part of the supersymmetry algebra. I don't know how many of you have studied supersymmetry at all? Could you raise the hand, please? Okay. How many of you have basic, I don't require so much, very basic knowledge of what superfields are? Oh, perfect. So, okay, so we can go straight. And if you don't know, please don't worry. Just go with the flow. Well, in general, this is how you do research, right? Just go with the flow. And then you will see that if you don't know superfield, all the lecture will make sense, I promise. Except that you might not be able to derive certain result in a convenient way, but just believe me on that part, and then we still can understand most of the part in the lecture anyway, okay? So don't worry about that, and yeah. So the structure of the course is on the note. It's about 80 pages. So the note actually serves many purposes. One of them is for you, if you don't want to take note, feel free. What I will write on the blackboard is precisely what will contain in here, okay? Secondly, there will be, because of the limited time, there will be no time to do all the examples. This note contains many, many examples, which I will not lecture. When I said, okay, this is given as an exercise, the solution is in here, or the reference in here, okay? So all the exercise have solution, I guarantee to you, okay? So you just flip to the right page, open, and then redo it yourself and compare the result with what's written here, okay? If I don't have time, I will omit some example, okay? So we can start now, actually. So we start from basic. So we'll first do the theory without gauge field first, and then we move on to the theory with gauge field, okay? So the most basic part I would like to start is chiral multiplet. So this serves as introduction of notation and so on and so forth, that you get familiar with the concept, and we move on in the lecture, okay? So a 4D n equal to 1 chiral multiplet. So if you want, this is basically the matter part of the theory, okay? Consists of a complex scalar, phi, a Weyl fermion, psi, let me put alpha. Alpha here is in this lecture I will use two component spinner. So alpha and alpha dot run from 1 to 2 as usual, okay? Right, and in the same representation of the gauge group, if you have gauge group. If you don't have, that's fine. They can be in arbitrary representation. Okay, it is represented by a superfield which I call big phi, okay? Satisfying d bar of alpha dot of phi equal to 0, okay? And has the expansion phi, big phi equal to, here's some resonance, okay? Maybe it's this spot. Phi plus psi alpha, theta alpha, plus f theta alpha alpha, okay? So this is the expansion. So you see that the multiplet, the chiral multiplet, contains scalar, contains a bifermion. This is the same bifermion here. The theta here is a supersymmetric coordinate, okay? And F is basically a non-dynamical field. This is auxiliary field, okay? This is non-dynamical, okay? It's just there. Well, and we can define the complex conjugate, which I call phi dagger. Well, it's antichiral. Antichiral means it satisfies d alpha phi dagger equal to 0. So opposite one with the chiral one. Okay, we will deal with the chiral most of the time, and this is the expansion. So this is usually called the bottom component, okay? This is next to the bottom, and so on. This is higher, and this is the superfield expansion, okay? This is notation we're going to use. Basically, this is the matter of the theory. Now you can ask, okay, what about the action? The effective action takes the form S equal to integral d4x d4 theta. d4 theta is d2 theta bar d2 theta, okay? This notation. K phi dagger plus d2 theta w phi plus complex conjugate. Okay, so this is the effective action for a single chiral field. Okay. Here, this is getting very, very important, and it will play a very significant role in our lecture, throughout our lecture. This quantity is a real function on phi and phi dagger. Okay? The real is very important here. Okay? This has a name, it's called Kähler potential. Okay? It's a real function. W, on the other hand, so if you want to have a picture, what I'm doing here, okay, I'll explain to you the following. You should think of Kähler potential roughly like a kinetic term, okay, for this chiral superfield. W, you should think of it like interaction of this chiral superfield. This is always the intuition you should have in mind, okay? So whenever I mention Kähler, you should think of it as kinetic term. Whenever I mention W, by the way, I'm sorry, this is a holomorphic function. Of phi. This is called superpotential. So there is a Kähler potential, a superpotential. Basically, you should think of this as kinetic term and this as the interaction term. Okay? So now you will see that the fact that this guy is a holomorphic function will be very, very highly important for us. Okay? Later in the lecture, you will see that basically the whole structure of this subject is building on the holomorphy of W. Okay? So, okay. Now for those of you who was unfamiliar with this language, now it's come to your comfort. I will write these things in components. So if you don't like superfield, if for some reason or not familiar with it, here it is. This is something that can translate you back to Peskin and Schroeder. Okay, so more explicitly, the action, you can write it as S kinetic plus S interaction plus S interaction dagger. Okay? Can people at the back see my handwriting clearly? Okay. When it's not clear, please shout, okay? And if you have questions, please do let me know. So where S kinetic term is this one. Has a G in front, d mu phi, dagger, d mu phi. Now you see, it's really kinetic term. Plus I psi bar, sigma bar, d psi. This is also kinetic term of the fermion, written in two components language. If you're not familiar, look at the appendix A of the note, okay? I translate it to 4 component language. It's a D slash. It's a usual thing, okay? Plus F dagger F and S interaction is like this. Okay, so let me define some notation. So you see that there's a So let me define the G and the dW, okay? So the G is basically the second derivative of K. I don't know how to solve this problem with the resonance. Maybe you have to put up with it. It's a toughness test. And dW is just a derivative of W of phi with respect to d phi, and d2W is basically d2W of phi, d phi, d phi. Okay? So these are the notation. This is sometimes called a Kähler metric. And then these are the expansion in component that you see. Okay? So there is something like a Yukawa term. If you want, this is in this interaction. This is big due to supersymmetry. You just expand the components. Okay, so this is the physics of it. And you see, this is why I say that you should think of Kähler potential as a kinetic term, and superpotential as an interaction. Now you see explicitly from this expansion. Okay, this is the intuition I would love you to have in mind. Okay. Okay. Now, this is going to be very important. It's a trivial thing. You learn, everyone learn. In 4 space-time dimension, which is what all our lecture will be about. Phi and psi have mass dimensions. Can anyone tell me in 4 dimensions what are the mass dimension of a scalar field and fermion? This you should remember. 1 and 3/2, yes. Okay, I will tell you why this is important, okay, soon. And so the mass dimension of W is 3, okay? This is important number. You can just put this thing in, okay, and count the dimension as usual. Okay, so this is will be important. We'll use this to constrain a lot of equation. You'll be quite amazed by how powerful this easy counting is. Okay? Right. Any questions so far?
You're working in Lorentz signature?
Yes, this is, well, okay. This, at the moment, will be Lorentzian. When it will become Euclidean, I will tell you. There will be some sloppiness going on, but I will tell you when I become sloppy, okay? Okay. Yes, at the moment, Lorentzian is true, yes. So, okay. Now, come to a very important symmetry. This is first global symmetry that I will introduce in the theory. This is called the R-symmetry. Okay? So any 4D n equal to 1 theory, not simply gauge, but also non-gauge theory, will have this R-symmetry. This is a global symmetry, okay? For 4D n equal to 1, it will be generically U1. Of course, as any global symmetry, this can go anomalous and so on, okay? So, but we will go to that point later. But this is the part. So, supersymmetry allows for a global symmetry, okay, known as the U1R symmetry. Okay, so now I stated, I have to state the action on the field, okay? It acts on the supersymmetric coordinate theta and W phi s theta goes to e to the alpha theta. So meaning that it has R charge 1, okay? In this notation, so it's rotated by the angle alpha, okay? D2 theta will be, this is Grassmann, D2 theta will be this because of the derivative, okay? So W will goes like e to the 2I alpha W, okay, because of the action has to be invariant. Is it clear? So from this you conclude that the superpotential has R charge 2. Okay? This is very important. Again, mass dimension 3 in 4 dimensions and R charge 2. Okay? This is something we're going to use repeatedly later. Also, a very important fact.
The fact that the specific coordinates change under this R-symmetry, does it mean also that the pilot spinor will have also transformed under this R-symmetry, or?
Yes, I will write it soon. Yes, this is your point. Thank you. Okay. So, indeed, as a member of our audience point out, it will act on a field, right? In a component of the field. So, this will be what I will state here. This symmetry acts differently on different component phi, psi, and f of the same chiral superfield phi. Okay, so suppose that if phi transform like this, R phi alpha, this means that the R charge of this thing is R, okay? From, oh, I erase. So you remember the expansion? Let me write it down. Recall that phi equal to phi plus psi theta plus f theta theta. You remember this equation? So can you tell me what's the transformation rule for psi? Will be r minus 1, right? Because of the theta. Okay? So this will be psi goes to exponential r minus 1 I alpha. F goes to e to the r minus 2 I alpha. F. Okay. You agree with this transformation rule? So, meaning that we write R charge of phi equal to R, R charge of psi equal to R minus 1, and R charge of F equal to R minus 2. Okay? So, for R symmetry, each component in the same multiplet follow from this rule. Okay? This is how they charge under R symmetry. Now, we declare that the R charge of the superfield phi is the same as that of the lowest component. So meaning that we assign R of phi to be the same as R of small phi equal to 1, to R, sorry. Okay. I hope this is clear. Okay. So this is the R symmetry. Okay, now come to abuse. Yes, please. Not yet. It can take any value for now. Okay. One of the most important is to fix it actually. Okay, but you have to give me a theory, okay? For at the moment, I will leave it general at the moment, okay? We'll discuss this issue later. Thank you. And abuse of notation. This is highly abusive, but it's abused through our literature. So if you read paper in this field, we always, the point is that when there's no potential confusion, sometimes the lowest component, you see in the Greek letter we use a small version versus capital version. Capital version is used for superfield. Small version is used for the lowest component. If there is no potential confusion, usually we write one for another. So we refer to chiral superfield as the lowest component and vice versa, and we never keep track of them, okay? So this is just abuse of notation, just to tell you that in the literature, people always do this thing, okay? Including me. So otherwise, we will run out of letter, because every time we use capital letter, we have to use small case for the lowest component, and you will see that we cannot be consistent all the time. But please ask if you want to know whether this is superfield or this is lowest component, okay? It's always clear from the context, okay? Right. Now, one of the richness of the supersymmetric field theory is the structure of the vacuum. Okay? Okay, now this should be mentioned clearly, I think. It's not emphasized enough somehow, but from the action here, let's write this as a star. Okay. Okay, from star, the classical equation of motion of F is this one. So if you plug it in, you see that the scalar potential is V of phi dagger equal to G F dagger F. Okay, this is G in. You plug this in, you get this. Okay. Right. So this is how you obtain the scalar potential. Well, this usual. This is usual. You use equation of motion to obtain this. Okay. Now, one of the most crucial points is that the supersymmetry algebra implies that the scalar potential has to be positive or zero. Okay, so let's derive this point. I will erase this board, I think. So let's provide the argument for this one. This we will use later also, okay? So let's derive it now. This comes from supersymmetry algebra. Okay, so let's do this. Argument. So what's a SUSY algebra? It just says that you have supersymmetry generator. I hope you know this, right? Equal to P alpha dot. I hope people are familiar with this. This is a supersymmetry algebra. Basically, implies that if you take Hamiltonian, this will be sum of alpha, Q alpha, psi square, plus the dotted version, and this has to be positive definite, okay? For any grounds, supersymmetric state psi, okay? So basically, this is the argument. So this is Hamiltonian, and therefore scalar potential contained in here. So it has to be positive, semi-definite, okay? So what is a constraint? So since this has to be positive or zero, we can talk about something called ground state. Ground state is the lowest energy, okay? So lowest energy means that, so the supersymmetric ground state meaning that these bounds are saturated, okay? So it's zero, are determined by the minimum of the scalar potential. Okay? So meaning that the condition for the existence of SUSY vacua is dw by d phi equal to 0. Okay? So this is the condition for the existence of supersymmetric vacua. Sometimes this has come in many names, okay? Well, because we derive this using the equation of motion for F. Sometimes this is called the F term condition. Okay, this is first name. Second name, some people call it F flatness condition. Some people call the solution of these flat directions this is called the flat direction. Some people even call this the moduli space of vacua. Okay, there are many names, okay? Please.
So is that condition due because the vacuum is annihilated by these supercharge? Is that the condition that we're...
Right, so basically you write H, right? So this is a Q2 dagger, Q dagger, Q. Yes, so basically this is the Hamiltonian and then you put this as square. So what's your question, sorry?
But if I goes to
Oh, to set to get the bound. Yes, exactly.
all right.
Yep.
Another question, because it seems that this also we have obtained this because we are using the superspace formalism and using this auxiliary field F. If, for example, I don't know about superspace and I just work with the scalar field phi, sorry, and the phi terminals, would they obtain this same constraint? Or?
Yeah, okay. Without this, you mean?
No, because this was at the beginning that the field F was a kind of auxiliary field to introduce for the expansion of...
Right.
Then if I'm not using superspace formalism, what happens?
You write down in components, you mean?
And I also arrive to the condition, to the F term condition.
Harder.
Okay.
Yeah. So you have to assume certain things. Like for example, you have to give me this type of action if you don't know superspace. But yeah, that's why I'm saying that if you don't assume some knowledge at all, this will be the missing link. This I think is the most direct derivation that I can give you. But it's followed from supersymmetry, I think.
Usually in the literature, the Hamiltonian space is the space when you have the d-term equation. In that case, you don't have...
There is no d-term yet because I haven't introduced the gauge field. Soon I will introduce gauge field, there will be d-term. Yes, you have to solve them together.
So, in order to avoid confusion, we usually refer to modular space even if we put d. I mean, it's not enough to put the F-terms equation to 0, right?
Yes, but since I haven't introduced the gauge field, this is enough.
Okay, in that case, we don't...
Yeah. So I will move on to gauge field, and I will tell you precisely that there will be another equation you have to supplement to this condition. This is called D-term equation. But wait until I introduce the gauge field. At the moment, this is fine as a moduli space of vacuum. You will see example actually. So I will give you two examples. One thing I have to emphasize. If 2.14, if this equation, let me call it double star. Okay. So let me emphasize this. If double star do not admit. Oh, by the way, I have to say that this is derived from, if you take this theory from this effective action without, well, suppose you start everything from classical, okay? So when you write down Lagrangian, usually you assume that everything is classical, is tree level. Then when you solve this thing, this is called classical supersymmetric vacuum, okay? So this is called the classical moduli space of vacuum. There can be quantum correction that can enter this thing, I should emphasize. So, but I will discuss about quantum correction part later. But this is important part of our lecture, okay? So at the moment, I just state this condition, just follow from the action that you write down, okay? Now, if double star do not admit a solution, the theory does not have a supersymmetric ground state. Then we say that supersymmetry is broken. Okay? This is important. Supersymmetry breaking is a really important phenomenon. Unfortunately, we don't have time to do it. But this is a big thing in the literature. So just to tell you that this is this condition. Actually, we'll mention some point later when we discuss about Witten index and so on. Okay? So, right. So now it's time to do example. This example will be very, very instructive to all of this. Even though you think this is all classical and so on, there's already some richness in this. Please.
But if you don't have a solution, is there any way to leave your theory, like to have a SUSY solution or not? Because it's not why it's SUSY broken. I mean, if I don't have
Well, if you don't have a ground state with respect to that symmetry, usually you declare that the theory doesn't.
But it's spontaneously broken, right?
Not necessarily. It can be explicitly broken also. The breaking of a symmetry can happen in many ways, okay? Two main ways is you add a term that break it. This is called explicit breaking. Where if you put sometimes you put an equation that respect all the supersymmetry algebra, but suddenly you find that there is no solution. This is called spontaneous breaking, okay? This is true for, in general, any symmetry. Also for supersymmetry. The subtle part of supersymmetry breaking is that how can you generate such a thing? Such a Lagrangian or quantum correction can help you break the supersymmetry or something like that. This is another rich subject to be discussed. But in general, if you don't have this solution, this means that supersymmetry is broken. Okay? Please.
You set it up now, it's all manifest. So it's spontaneous breaking the way you write it now, right?
Yes, so okay. If I assume that my action has supersymmetry, and then I said, okay, I don't find this, then okay, you can declare it as a spontaneous, okay? That's fine. So the simplest one, I think, is called O'Reilly-Fatty model. This you can have a look in the literature and see. This is one of the simplest model of a supersymmetry breaking. But in this course, we assume the supersymmetry is preserved. Well, not assume, we will check it, of course. There are many methods to check it. I will derive it later. One of them is, for example, with an index and so on. We will mention this point later in the course, okay? At the moment, Okay, we will check that at many levels, supersymmetry is preserved. And we will deal mostly with the supersymmetry preserved model, okay, in this lecture. Any other question? For example, if you give mass unequally to fermion or boson, this is one way to break supersymmetry easily, okay? So you just turn on mass parameter differently for fermionic component psi or bosonic component in a different way. This is called a mass splitting, right? This is one way to break it explicitly. Yeah. Because supersymmetry has to transform fermion and boson in the same multiplet. Therefore, the whole thing has to transform together. If you try to separate them, then this is one way of explicitly break it. Okay, so let's come to example. Example number 1. This is called the Wess-Zumino model. What time I have this until? 20 minutes, okay. Okay. We assume K to be phi dagger and W to be 1/2 of m of phi square plus 1/3 lambda cube. And analyze classical vacuum. Okay, so at the moment, we assume everything is classical, okay? Okay, so let me point out one thing. Even classical physics of this model is super interesting, I can assure you. First, look at this. I declare that W is holomorphic. Now, if you are very careful, you can ask me already at this stage, what about M and lambda? If they're holomorphic, they have to be complex. Right? Cannot just be a real quantity and then I declare this thing to be holomorphic. Indeed, in supersymmetry, let me tell you from this state, you should promote all coupling, including mass, M. I will tell you why it's mass. And lambda, promote M and lambda to be background field, okay? So this is usual. Those of you who did some course in QCD probably have seen this thing. Think of this as a background field. Background means non-dynamical. They're not dynamic, meaning that in the path integral, you don't integrate over them. Okay? And since it's supersymmetry, you should think of it not just a normal background field, but background chiral multiplet. Okay? So it's like a superfield, basically. But think of it as background. No, they're not dynamical. Okay? Just a word of this. Okay, then it's consistent, this picture. So you can make W totally holomorphic, and you can use power of holomorphy to constrain a lot of things. This point will become clear later, but just to tell you this thing. So, okay? So, this model, if you expand component, has Yukawa coupling, lambda phi psi, and aquatic interaction. Lambda square phi, oops, sorry, to the 4. Okay, so those of you who doesn't like superfield, this is if you expand it, you will see this term. Okay? So, now let's analyze the vacuum. From W phi equal to M phi plus lambda phi square equal to 0. Oops. This is the F term condition, right? Take derivative with respect to phi, okay? You get this thing. There are two classical ground state. Namely, phi equal to 0 and phi equal to minus m over lambda. Do you agree? This is just solving this equation, okay? There are two solutions, okay? However, now you can ask, are these two vectors equivalent or inequivalent? Now here comes the interesting point. Under transformation, phi goes to m over lambda minus phi, which exchanges the two vectors. W transform as W goes to minus W up to an unimportant additive constant. M square, m cube over 6 lambda square. Okay. So what I claim is that you can do this transformation, okay? Then what happened is that you change the sign of W, and there is some constant which you can, is not important because it's just a constant in this interaction, okay? So what happened here? So meaning that these two vectors are related up to a change of sign of a W. Now, what I'm going to show next is that you can even rotate this sign back using R-symmetry. Okay? Now, this generates a very important symmetry, actually, in the theory. So let's see. Because W has R charge 2. The sign of W can be rotated away. By U1R symmetry. Okay, if you remember, W transform as e to the I2I alpha W, right? How do you rotate the sign away? You just set, for example, alpha equal to, say, minus 3 pi over 2. With alpha equal to minus 3 pi over 2, for example. You agree? This rotates the sign of W away. Okay, so fine. So now let's determine the leftover symmetry. Because now you see that two vectors are related by a sign of W. Okay, now you can use R-symmetry to rotate it away. So what's the symmetry? So suppose that we take R of phi to be R equal to 2/3. Okay? At the moment, this doesn't fix anything. It's just our choice of value. There's nothing to fix it for me. Okay? So R of m equal to 2/3 and R of lambda equal to 0. Okay. So this put in bracket. Okay. This maps phi to e to the minus 3 pi over 2 r. Okay. So I plug this value of alpha, plug it in here. I have minus phi. You agree? And psi map to e to the minus I 3 pi over 2 r minus 1. And if you do algebra, it will become I psi. So if we fix value of r, you will see that phi goes to minus phi, and psi goes to I psi with this value of r, okay? With this value of alpha, okay? Does you agree? Okay. Of course, if I fix r, what we have here is that, now you see that if you square, this will become itself. But if you square, you have minus psi, okay? So this generates a Z4 symmetry. So once you choose this value of R, you break U1R symmetry to Z4. Okay? Because you fix the value of R. Okay? Now you understand why it's Z4? Because the generator of Z4, you have to take it to power 4 to back to identity, right? And indeed, you have to take it to power 4 to map phi to phi and psi to map psi to itself. Okay? So this generates C4 symmetry. Okay. So indeed, if we raise it to the power 4, you go back to identity.
So you mean that for general cases are...
No, this is the special value of this.
in the case of the general case of R, you entirely break your U1.
Yeah, once you fix the value of R, you will generate, because you pick the value of a specific value of charge, okay? But this is classical, by the way. Nothing constrains us at the moment to which charge I can.
This one R-symmetry is something that comes from the method procedure. The one R-symmetry doesn't come from something that is method procedure.
Come from?
Does it come from the other theorem? Does it come from that?
The other theorem? Another theorem. Another theorem just say that it's a conserved current, okay? Is that another theorem just say that if I have a symmetry, I have a charge. That's why when I assume that there is R-symmetry, I have U1R charge.
But does it want to take the charges for you, or can you just pick the charges as you want?
No, this thing I can pick it. It's consistent with whatever I analyze. There's no such a thing to constrain it at the moment.
Is there a special value for R with which we can recover a bigger loop than Z4?
The Z4, okay. Yes, there is. If you pick a value of R, this is not a manifest choice. But if this is the value, then you see that there is this symmetry generated by Z4. Now, what is more important is the following. Now you see the phenomenon of a spontaneous symmetry breaking, actually, of Z4 symmetry. Now let me erase this. So let me note that you might ask, okay, so what's the consistency that I have? I don't have any constraint apart from that my superpotential has to R charge 2. And indeed, if you set R of phi become 2/3, R of m and R of lambda has to follow from that because my superpotential has to have R charge 2. That's the only constraint I have from classical physics, okay?
But have you assumed that n and lambda are not vector?
Of course.
Otherwise,
That's why they can carry the charge.
I see.
And this is also consistent with the fact that superpotential has to be holomorphic.
But does supersymmetry really require that it's holomorphic?
Of course. This is why you should always think of coupling as background field. Okay. Yes, it's not emphasized, but if you listen to, for example, Professor Seiberg, this is the thing that he will preach from the first lecture, that this is a thing that you should do. And indeed, otherwise you cannot assign charge to this thing naturally. And assigning our charge to these objects are highly important, okay, for our business here. Now, in each vacuum, whether you pick phi equal to 0 or phi equal to minus m over lambda, Z4 symmetry is spontaneously broken to Z2. Why is that? This is because the transformation phi goes to phi and psi goes to minus psi. Leave each vacuum invariant. Okay? So what I would like to emphasize is that you have symmetry Z4. Okay? But then if you go to each vacuum, this is what I want to emphasize. I picked this example to carefully explain to you that phenomenon of spontaneously breaking, you have to talk about vacua. Okay? Once you determine the vacua, you go to that vacua and you expand around that vacua. You assume you see that symmetry is smaller. Then this is the phenomenon of spontaneously breaking of symmetry. Okay? Now, what about Z4? Z4 is still there if you're not in the vacua. The generator of Z4 relates the two ground state. Its square acts as a 2-pi rotation in, oh, I don't know, you see it? The Lorentz group, SO31. So this implies that C4 is unbroken. Okay, can you see the upper board? Oh, the last line is a bit, okay. So what I'm saying is that the Z4 is still there. Spontaneous symmetry breaking doesn't mean that the symmetry is not there. It's simply that if you go to each ground state, this is broken, of course, but this symmetry is still there to rotate ground state. This is what I would like to emphasize. Okay? And how do I know the Z4 is unbroken? Because I square it. It's a rotation of Lorentz group. Why? Because Z4, if you remember how it acts, it's if you square, phi goes to phi, psi go to minus psi, and indeed 2-pi rotation in the Lorentz group map scalar to itself, but psi to minus psi. Okay, is that clear? So, what I would like to conclude from this example, this is, by the way, classical. I haven't done anything quantum mechanics. Okay, this is a classical phenomenon. This classical phenomenon, I just constrain my R charge using algebra, meaning that superpotential has R charge 2, and that's it. Okay, there's no, I haven't said, oh, this R charge coming from quantum mechanical effect, coming from whatever quantum effect. No, this is simply from algebra. Okay? And I assume what you see is what you get from the Lagrangian. So again, this is very classical. We will do quantum mechanics of this model later, okay? So these two vacua are said to be physically equivalent. Since there is an unbroken symmetry that relates them. Okay. Perfect. So, any questions so far for this model? Any of you who are expert in this business of 4D n equal to 1, soon you will see a very similar example when I introduce gauge field. This is called 4D n equal to 1 pure super Young-Mills. Okay? It's exactly the same argument except that quantum effect is much stronger. This is classical analysis, but the analysis will carry through. That you, in each vacua, you have spontaneously broken, but then each vacua still have symmetry that relates them. Okay? Soon we will see this example. Once you choose the R charge. It's a global symmetry, but I choose the R charge explicitly.
Like sort of gauge fixing by choosing the R.
Yeah. So I exactly choose the fix the R. Yeah, that's right.
So basically nothing else you would choose an R, right?
No, in general, no. It's just that I have to choose it such that superpotential has R charge too, because that's the requirement of algebra. Otherwise, I break even the algebra of what I assume. Okay?
So then I should choose another variable.
You can.
And then everything goes through, I get the same physics.
No, so that's the phenomenon of different choice of what the charge you choose. This is and this analysis is very specific to this choice.
But they always physically equivalent, depending on.
Yeah. The important part here is that the sign of W can be rotated away. This is the important physics, okay? So now let's move on to example number 2. This people call the LH model. L stands for light, H stands for heavy. Okay? So what is this theory? You assume that now there are two kinds of superfield, L and H. That's why I call LH model. With the Kähler potential, LL dagger plus SH dagger, and W equal to lambda over 2 LH square. Okay? So this is my model. Again, we do classical analysis of this model, okay? Why do I introduce this model? I want to show you that this model has a feature that you can integrate out some field, some heavy field. So the H are our heavy field. So, okay, so how do we see that? Okay, so first of all, we analyze the vacua. Let me write it like that. Lambda H square equal to 0. The H of W equal to lambda LH equal to 0, okay? So the minimum of the scalar potential V of L, let me write it like that. L squared H squared. Too many modulus. Okay. Fine. Is achieved at H equal to 0 and L arbitrary. So you agree with this? This means that the H equal to 0, L can be any value, okay? So since L is a superfield, right? Bottom component is scalar. It's arbitrary means that it can gain any vacuum expectation value in this vacuum, okay? It's like a Mexican hat. You can, well, in this case, it's even arbitrary. Whereas H is fixed to be 0 by this vacuum. So it cannot gain any value. It has to stuck there. So in this case, you see that L is massless, which we call light. And because massless field can gain any vacuum expectation value. H is has mass m of H. Let me write it like that. So L is massless or light, whereas H has mass m of H equal to mod expectation value of L times lambda. Do you agree with this? So this is why we call heavy and light and heavy. Okay? So now the moduli space is what? H, we have two scalar fields, the bottom component of L and the bottom component of H. H is fixed to be 0. L is arbitrary. So the moduli space is one complex dimensional, parameterized by expectation value of L. Is it clear? This is remember, it's not real dimensional. We are in supersymmetry. It's a complex scalar. Therefore, everything is complex. Okay? The moduli space of vacua. You see now I really use the word moduli space of vacua is one complex dimensional, parameterized by vacuum expectation value of L. Okay? And at each point on this vacua, there's no symmetry that relates them, right? In this is easy to analyze. There's no symmetry that related them. So these vacua are inequivalent. So it's a complex line, if you want, or a plane complex. You think of it as anything. Okay, but there at each point on this line, on this complex line, there's no symmetry that relates them. So okay, So this is the two examples of the classical physics I would like to tell you. First one, we have two classical vacuum. Only point, Wess-Zumino model, we have 2 points. But 2 points are related by symmetry, algebra. It's followed from algebra of supersymmetry. Second one, you have continuous vacuum. It's a line. It's a complex line. Of course, each point on this line is a vacuum. Okay? This is the nature of the theory that we're going to analyze. Sometimes vacuum can be discrete. Sometimes vacuum can be continuous. So, and you have to analyze case by case. Okay? So this is the physics of the classical vacuum. But everything follows from dw by d phi equal to 0. Okay? So that's the conclusion. Right? Any question?
Yeah, I have a question. So the vacuum is equivalent.
Yeah.
But I mean, there is, let's say, kind of equivalent classes of equivalent vacuum. There's, I mean, subgroups of.
It's a space. Okay, it's a C basically in this case. So of course you can talk about isometry of this vacuum. Okay, C has some isometry. Some more complicated model has more isometry. Of course, it is interesting to talk about isometry of those, but at the moment, yeah, from point to point, once you fix it, there's no transformation. It's unlike the first example. W goes to minus W has a transformation that make you go back. Here, no. That's the main difference of the two examples. I hope these are instructive enough. I mean, I try to pick carefully the example that, yeah, quite sophisticated. Even classical physics is so sophisticated. Now, once you understand classical physics, we then can move on to quantum physics, okay?
Could we take the L to be minus its step and rotate away the sign from the superpotential?
The minus of itself,
We could take half of the moduli space and minus the vector and map one to each other.
okay, in that case, if you take L to minus L, okay, the point is that this is the difference from this one. So, okay, of course, this is more like an isometry that you can do on the, but once you pick the value of L, you break this, you break basically the spontaneous, you put an L. There's no, this is important. When you go to one vacuum, there's no symmetry that rotates vacuum. This is unlike R-symmetry in the first example. R-symmetry doesn't do what you want to.
The point is that then you cannot have a symmetry right here. You cannot shift lambda.
You cannot shift lambda, that's the point. Yeah. Mm-hmm. So, does it make sense for you? So good. I don't know, what's the time now? How much time do I have left? Up to 1:30. Ooh. We can have a break now. So next, we will do non-renormalization theorem on superpotential. And if you have any question, you're welcome to ask me. Okay? Oh, yeah. Okay, so shall we resume? So, okay, there were some questions during the break, so let me go over them. Some of them are really good. So, first of all, this is abuse of notation. These are superfields. These are bottom components. And I use the same component. This is, okay, I cannot help, I'm sorry. But this is first one. Second one is, thank you, Davide. He pointed out to me. So let me be clear. In the first example, the two vacua are related by the sign of superpotential. Okay, W goes to minus W. Okay. Of course, there's symmetry that rotated back. This is why already two vacua are equivalent. Okay? Z4 is an artifact of this thing. There's a symmetry that I can assign, basically. This is some people call this spurion symmetry. If you have done this thing, this is basically spurion. You can come up with this kind of thing. And you can use this symmetry to constrain a lot of the dynamics, which now is the topics of the next one. Okay? I will explain to you what spurion means. Okay. Okay. Yes, light heavy.
Something that happens when L equals to 0. Because in that case,
it's the origin, yes. It's the origin of this moduli space. Thank you. It's a singular point. So all the field become massless there. That's a usual stuff. You wonder what happened? No, it's a good question. The point is that I can even tell you that this becomes 0, right? At that point, yes. Usually this is a singular point on the moduli space where all the field become massless. Usually it's quite important in that something becomes singular there. You need to, quantum mechanics can play into important role and this kind of thing. But yeah, it's the origin. Every field becomes massless there. That's true. I have nothing to say in the classical picture. Okay. Okay, now let me tell you the next topic. This is a non-renormalization for the superpotential. Many of you who did supersymmetry will know already this result. This result just say that the superpotential doesn't get renormalized in perturbation theory. Okay, that's it. This is the statement. Okay, so let me erase this. And you understand the physics of the assigning charge better from this example. Okay. So, okay. So this is the one-line summary of this theorem. Okay. Well, as in physics, theorem is stated loosely. So, okay, and the proof will be also very loose also. Okay, so let me state physics here. First of all, this result just say that whether you do loop computation, okay, in coupling, there is coupling, right? So you can do loop computation in quantum mechanics. At all order in perturbation theory, superpotential will not get renormalized. This is the theorem. This is a very old result, by the way. It's not a new result. It's in since 1979 by Grisaru, Siegel, and Martin Rorschach. They use a so-called supergraph technique to prove this. Okay, so this is a very old result from 79, but we're not going to do that. We're going to use technology due to Seiberg. This is very standard by now in this field. This is in 93. Okay, you see that there's a gap, a huge gap of understanding of this thing. So what's the technique here? The technique here relies on one thing. So namely that first of all, think all couplings as expectation value of some background superfield. Okay, this we have done roughly, but now I'm going to emphasize this point again. Okay, so m or lambda, when you talk about which mass, you should talk about it as a vacuum expectation value of some background field. Okay, now we also have the second one, that this is the first principle. Second one is that under Wilsonian renormalization, the effective superpotential is holomorphic. Not only in effective field, but also in couplings. So what we assume here is that holomorphy stay under renormalization group flow. You can ask, oh, how can I justify all of these points? Not really. But there is some part you can justify in lots of theory that there's no, well, people say that in 4-dimensional there's no holomorphic anomaly, in the sense that if you assume the holomorphy to stay, quantum mechanics never break this holomorphy. Okay? So this is what we're going to assume in 4D. But you have to know there is some caveat here. I assume that this proof is without caveat. Okay? And once you assume this, if you were really strict to me, you'll come to me later. Which renormalization scheme do you use? Okay. This is a subtle question that I have always assumed that there is a scheme in renormalization that preserves this holomorphy. Okay? This is going to be underlying assumption. And once you assume this, we're going to proceed. Okay. So, let's take an example. So, let's pick our favorite classical. By the way, I'm talking about only non-renormalization theorem for superpotential. Superpotential doesn't get renormalized. This is not true for Kähler potential. Okay? Kähler potential get renormalized heavily. This superpotential doesn't get renormalized in perturbation theory. Oh, and another remark is that it can get renormalized non-perturbatively, by the way. This is a result in perturbation theory only. Okay? So, let's assume that, okay, the Wess-Zumino model. Okay, we will focus only on superpotential for now. Kähler potential is completely different story. Okay, so superpotential, classical. Now we're going to do quantum mechanics. So this is important to write this classical explicitly to be half m phi square plus 1/3 y phi cube. So the goal is to find the Wilsonian effective superpotential of this theory. This is our goal. Okay? So what are we going to do? So again, first we promote M and Y as background field, as usual. This is point number 1. And then we start assigning charges to the field. Okay? This is some people call spurion symmetry. Okay? This word already there in QCD and people use it all the time, but let's apply it here, okay? So, 1, promote M and Y to background fields. And now we can assign charges to them, okay? In the same way that we did previously. Now it will become explicit for you. So there are 2 charges actually you can do, okay? First, there is something called U1 phi. What does U1 phi do? It assigns charge 1 to phi, meaning it rotates e to the I phi, e to the I alpha to phi, okay? And to all the components in phi, okay? And there is a second one. Can anyone tell me? R-symmetry, okay? Such that you can assign any value to this, such as superpotential has R charge 2, okay? No constraint at the moment, okay? So, as I said, there's U1 phi and there's U1 R. So, and there's a field phi, M, Y, and superpotential. You agree with this? This is our field, and this is superpotential. Okay? Up to you. You want to do which one first? Let's do phi. So U1 phi, by definition, I have to give charge 1. Otherwise,
So how do the Grassmann variables of the superfield transform under this U1 phi?
0.
0.
The point is that any global non-R, this is what I will start this word soon. Superpotential is always neutral because it's in the action. If you look at the expansion of the action that I see, superpotential has to be neutral under the non-R symmetry. Okay? So any charge that you assign has to be 0. And usually this, because supersymmetry doesn't, well, this is not supersymmetry, right? It doesn't tie with supersymmetry. This thing doesn't act on the supersymmetry coordinate. Only R symmetry can act on it. Okay? So we know that this has to have R charge 0 and this has to have R charge 2. Okay? Good. I come up with this charge so that this guy always have R charge, phi charge 1. That's why I call U1 phi. Okay? And if you have 2 fields, phi 1, phi 2, you can assign U1 phi 1 and U1 phi 2, such that U1 phi 1 has R charge 1 and 0 for U1 phi 2 and so on. Okay? This will come up with example with many fields, but let's do one field for the moment. So we assign, this is by definition, by construction of our phi symmetry. You might say, but is this a real symmetry or what? Okay, this is why it's called spurion. You can come up with it. It can be spontaneously breaking, it can be breaking, it can be explicitly, well, you assign it such that it's compatible with superpotential. So it's there. Yeah, but you come up with it. Whether in quantum mechanics it will become anomalous or something, that's another issue. Okay? But you can always come up with this symmetry. To each field you can assign U1 such that this guy has R charge 1. In quantum mechanics, the fate of it under quantum theory will be another story. Okay? Is it clear for you? This is called spurion symmetry. Okay, if we assign phi to be 1, what's the phi charge of M? Minus 2. What's the R charge of Y? Minus 3. Excellent. So we have this. Okay? Right. And now for the U1R. As I said, U1R at the moment we have no constraint. The only constraint is that superpotential need to have R charge 2. At this moment we do it at classical level, okay? We use it to constrain symmetry. So for convenience, I will assume that his R charge 1. And if this has charge 2, what's the charge of M, 0, and this has R charge minus 1. Okay. So this is my table of charge. And we will use U1 phi and U1 R to constrain my dynamics, okay? So let me explain here. So for those of you that find this a bit too fast, let me write it in words, okay? We take U1 phi Okay. Right. So now we assume that the W effective. So observe that now we have two types of superpotential. This is classical level. This is the Lagrangian where we started with before renormalization group flow. Now we turn it on, the RG flow. We ask, what is this? We assume that it has to be holomorphic in phi, M, and Y. Okay? So what's the most general form you can write down? You can write down it as M phi square F of Y phi over M. Okay? What are these? Y phi over M is something that is neutral, okay, under both symmetry. And F is a holomorphic function, where F is a holomorphic function. And T defined as Y phi over M is a neutral quantity. You agree with this? Look at table of charge. Okay, and this has R charge 2, W effective.
Sorry, if M is a superfield, what's the meaning of dividing the superfield?
This is a, well,
I don't know, taking it as the
expectation
expectation value.
value. Yeah. Yes, you might argue again that the second, how you call it, double layer of sloppiness is not to put bracket all the time. I'm again very sorry, because indeed, if you put bracket all the time, by now the blackboard will be full of useless notation. Yeah, so apologize for this.
So it says we'll take the UN phi charge, and what's that word?
A what?
On the first line it says we take the UN phi charge.
UN phi, oh. We take the U1 phi charge of phi and the U1 R charge of phi to be 1. Okay, thank you. Okay.
So it's important that T is a dimensionless parameter, right?
It's the neutral quantity.
Also, I mean, under dimensional analysis.
Ah, yeah. Wow. Yes, you can. Yes. So indeed, there are I will provide this that soon actually. Do you want to talk about that? Yes. So, thank you, yes.
Statement is that's the unique choice.
Yeah, constrained by both mass dimension and neutral charge. Even neutral charge, you can already come up with this, this thing. Okay? Are you ready? Good. So now we talk about F. As y goes to 0, I erased the classical. Okay.
Sorry, if you have a SUSY backdrop, is it bizarre what the arbitrary flow? No.
It can be lifted. This is not guaranteed. Nothing in life is guaranteed under that. Apart from that. Apart from this, whenever there is non-renormalization theorem, you get some insurance in life, basically. Yeah. So here, as y goes to 0, the theory is free. Well, if superpotential is perturbatively is fine, right? But non-perturbatively, there can be correction to superpotential. Then you're not guaranteed to have vacua anymore under non-perturbative effect. We'll come up with that. This is called Affleck-Dine-Seiberg superpotential. This will be in the later part of the lecture. But before we get to that, let's do this example. As y goes to 0, the theory is free. You agree with me? We only have mass term. So it's a scalar with a mass term, so it's free. Okay? This implies that no negative power in phi. In f of t. Okay? It's a free theory. You cannot add anything like that. Okay? In f of t. Because we want to keep it a free theory. As m goes to 0, we don't want the theory to blow up. So f of t contains no power greater than 1. Okay, so this is the first point, second point. Now come to third point. W effective has to match W classical at weak coupling. Of course, meaning that when you set y to be close to 0, you have to recover the W classical back, okay? Because, well, if you set to weak coupling, it has to be the classical superpotential. So Ft has no other powers than 1. Okay? So this means that f of t has to be this form. This is to match the classical one. And there you go. W effective is therefore equal to W classical, as we want to show, right? And the superpotential is not renormalized. Okay, at this point I should mention certain thing. This method of using charges to constrain superpotential and so on also not just work for perturbation theory, it also works for non-perturbative physics. We will see actually, I will use the same technique to constrain superpotential of many non-perturbative phenomena. So this assigning in charge look very basic, it's extremely powerful, okay? Because non-perturbative physics, actually in various dimensions, not just in 4 dimensions, 3 dimensions, 5 dimensions, you use a similar technique to constrain charge in this way. And then you say that it has to be compatible with symmetry and so on. And you can even predict the generation of the non-perturbative physics using simply this analysis, okay? So, but in this, for this purpose, I'm just saying that, okay, it's not renormalized, and I don't put any comment further. Well, because it can be used to constrain non-perturbative physics also. Okay, but perturbatively for sure, there's no correction. Okay? So this is the important thing we want to show. And another remark is that no claim about the Kähler potential. To spoil the episode, I should tell you that there is correction to the Kähler potential. This will be the next lecture. So I know that we run out of time, but if you manage to let me squeeze second example very briefly, 5 minutes, okay? You hungry? Yes. But okay, let me squeeze the second example and then we done, okay? So it's a natural continuity. I'm sorry about that. Okay. In fact, I changed my mind. I'm kind. So let's stop here and then, well, let's be on time and then we continue with next lecture, okay?
Lunch is served just out.